Hello and welcome to Insanely Huge Numbers, and this is episode 1. I know I've done this series before. In fact, that's actually 3 times. This is 3 times. The third attempt to do it because last 2 times it really doesn't hit the expectation I have for myself. Yeah, so as you can see, I've changed a media and then I've also got a new laptop, so yeah, I hope this time is gonna work out and I will actually get into the depth of these huge numbers. But in case you don't know what I'm talking about, watch my previous videos on the subject of big numbers. Also, I think my computer is glitching out right now because it's having these weird font bugs, but I think that's gonna be fine. Let's begin this lesson. Alright. So this series is gonna be about, big numbers. But before we really get to the truly massive ones, let's set our expectation high with some numbers that is not as big as the ones that we will talk about, but still big nonetheless. Begin. Now we got one. Um, that's one, and that's two. Those are not really massive numbers, really. It's not gonna shock anyone. 10. You have 10 fingers. You might have you might have 10 toes, but maybe you don't. 100. Yeah, and 1,000. That's quite a bit of numbers. And there's 10,000, which is 10 to the 4. And in case you don't know what that means, 10 to the n means 1 followed by n zeros. So there's 1, 2, 3, 4, 4 zeros. And 10 to the 5, that's 100,000. Yeah, that's pretty insane. Big number. If you have $100,000, you will probably be called rich. I mean, not the richest man on earth, but pretty rich. 10 to the 6, 10 times richer than before, and then 10 to the 10. That's a lot richer than before. Specifically, you're 10,000 times richer than 10 to the 6. So, yeah, let's see how big we can get. 10 to the 100, which is a Google, as some of you might know, but I don't think most people know this. So Google is 1 followed by 100 zeros, and that's you can count it if you want. That there is indeed 100 zeros. Now it's 10 to the 100, 10 to the 1,000 actually, which is Google to the 10th, and yeah, it's 1,000 zeros. Now next we got 10 to the 10,000, which is gonna be 10,000 zeros, which is it's a pretty big number. All right. By the way, this is Google is far more than the amount of particles in the universe. Those are 10 to the 80, and this is 20 orders of magnitude bigger. So yeah, quite impressive. And these just completely blow this out of the water. And then we got 10 to the Google, which is known as Googleplex. I don't know why I didn't write it, but yeah, it's 10 to the 10 to the 100. And this number is quite insane in the way that if you write a zero, if you treat each particle as a digit, you will not be able to write this number out in the entire universe if you write it in its complete decimal expansion. Right, so you will write it as 1000000. If you use up all the particles in the observable universe, you're still not gonna even approach exactly how big this number is. Alright, so that was a nice intro, I hope. And so now, what we're gonna do next. And let's introduce a level operators. It's not a level operators. It's leveled operators. So they look like this. L of a b c. This is a function, or alternatively, which I prefer is L sub a of bc. Now, notice how there's a nice progression from addition to multiplication. Well, it's actually not that nice, but addition to multiplication to exponents. So multiplication is a times b equals a plus a plus a plus a plus a, right? Which is you're adding a to itself for b times, and the exponent is that, but with multiplication. So maybe we can generalize this behavior with our level operators. And let's get to defining level operators, because why not? Right, so here's the definition, and L sub c of a1 is just going to be equal to a. This is to mimic the a times 1 or a to the 1 behavior, so it just returns a. And then, so for example, L of 100 of 3 of 1 is 3, alright? And then L of 0 of a0 is equal to a, right? Because this is supposed to mimic addition. 0 being the 0 being the additive identity. So you get L sub 0 of 1 and 0 equals to 1. And then this is L sub 0 of AB, so that is equal to L sub 0 of A of B minus 1 plus 1. So this essentially just takes this number, subtract it, and then put it on the L side, so we can actually evaluate it. Now, next, this is the most important rule, I believe. And then, so it's just saying that we take this level, right? Let's say we have C, level C, and then we just apply level C minus 1 with A as its first input, and then use the whole entire level C operator with the second input minus 1. So yeah, you can see. I'm gonna show you how these rules work. So how big are these? I mean, how strong are these? Right. So L sub 0 of A and B is aiming to mimic addition. As you can see, if you try a few examples, you can see that it roughly, I mean not roughly, it exactly is addition on natural numbers. And then you have L sub 1 of A2. Let's work this example, alright? So you got L sub 0, which is A plus something, A plus L sub 1 of A1, A and 1, which gives you A plus A, which is 2A equals A times 2. So L sub 1 of AB is A times B. And you can actually prove this by induction really easy. Um, yeah, you can prove this by induction using the piano axioms. And the piano axiom is the definition for addition, right? And then L sub 2 of AB is repeating L sub 1, which means that it's A to the B, since that's a few slides ago, that's gonna be exponents, which is the behavior we talked about. So now, what is L sub 3 of A and B? So let's try to compute it. Alright, so L sub 3 of 2 is L sub 2, it's level 2 operator with 3, and then and then level 3 operator with 3 and 1. So that's 3 and 3, and that's 3 to the 3. If you don't believe that the L sub 2 is actually exponentiation, then check out this computation. You can pause it if you want. And yeah, another example. This is a bit more impressive than 27. So yeah, let's you make it so that L sub 2 of AB is written as A to the B for the sake of easier understanding. Because it actually exactly follows exponential behaviors. L sub 3 of 3 of 3 is of 3 and 3 is 3 to the L sub 3 of 3 and 2, which is 3 to the 3 to the L sub 3 of 3 and 1, which is 3 to the 3 to the 3 equals 3 to the 27 equals this number, which I actually don't know how to pronounce. I think this is in the trillionth, so it's 7,6,255,974,848,087. Alright. And this one will probably blow your mind. Yes, this one is actually quite big. So you get 3 to the L sub 3 of 3 and 3. So notice how we already computed this monstrosity. And so we can just plug it in, and then we get this expression, and then this is 10 to the 10 to the 12, which is 10 to the a trillion, 10 to a trillion, and yeah, it's really hard to write because you actually cannot write it at all. You cannot write it. Well, actually, this is smaller than a Googleplex, which I've shown you before, which is 10 to the 10 to the 100. But if we just increase this by 1 again, it's gonna blow this out of the water with another layer of exponents. And yeah, this is where this episode ends. This is an introduction episode. The next episode will cover higher exponential towers and then go in depth to level 4. Actually, not really going to depth. We're just gonna roughly talk about it. And yeah, I hope you enjoyed this one. If you like this content, please consider like, subscribe, and hit the bell. Yeah. See you next episode.